All right, sorry, I was just minimizing the screen there. All right, thanks again, Devaditya, for the kind introduction. Happy to be presenting here for the EDS Society. So my name is Nidhin Kurian, and I'm an assistant professor at Arizona State University in the School of Electrical, Computer, and Energy Engineering. And the title of my talk for today is Gallium Oxide for next generation power switching and RF electronics. So it's going to be focused on gallium oxide. The work is primarily my PhD students Advait, Nabasindhu, Abhishek, who was a former master's student, currently at TSMC, and our undergrad student, Julian. And I will also acknowledge our collaborators from Agnitron for the in situ etching related studies, and from Dr. Hari Nayar's group at Cornell University for MOCVD growth. I'll also acknowledge our funding sources. So ASU, this is related to the faculty startup, and then the NSF award and the Army Research Award, specifically the Ultrawide Bandgap RF Center. Right. Yeah, so this is a brief outline for my talk. So I'll start with an introduction, particularly focused on gallium oxide and let's say ultrawide bandgap semiconductors. And then I'll move on to, so I'm primarily going to talk about, I guess 3 different, work that we've done recently. One is about a new technique that we've developed for etching gallium oxide, which is an in situ and a damage-free etching technique that we've developed. And then I'll talk about engineering of nickel oxide, gallium oxide diodes that can achieve low turn-on voltages and high reverse breakdown performance. And finally, I'll end with our recent work on fabrication and engineering of submicron FinFETs, and this is particularly focused on high-frequency transistors. All right. So just to give a brief background about my group. So we're mostly a device-focused group, and currently the materials that we're primarily interested in are gallium oxide. So that's kind of a workhorse material in our group. But we're also interested in ultrawide bandgap nitrides, which include AlGaN, aluminum nitride, and we also have ongoing work related to diamond electronics. And our primary areas of expertise is in epitaxial growth. So in our group, we currently have the capability for MOCVD growth of nitride. So we have a nitride reactor. We also have MOCVD growth capability for oxide. So this is for so that's an oxide reactor. So we have 2 reactors for epitaxial growth. We also do quite a lot of device modeling, and our primary area, which is device engineering and device fabrication. At the circuit level, packaging and circuits, we're really looking for open collaborations, right? We collaborate with faculty with expertise in this area, trying to sort of really understand, once we fabricate these devices, how does our device perform, and we actually sort of translate that into a circuit, right? So that's just a brief summary of what our group, the kind of work that we do in our group. Okay. So the primary application space, or primary application for many of these ultrawide bandgap semiconductors, including gallium oxide, is in power switching or power electronics applications. So on the left, I have a schematic to sort of easily understand, okay, what is the real advantage of using ultrawide bandgap semiconductors, right? So for example, if you move from the left device, so it's just a one-dimensional schematic. So for the left one is, let's say, silicon with a breakdown field of 0.3 megavolt per centimeter. So if you move away from silicon to, let's say, an ultrawide bandgap semiconductor like gallium oxide with a much larger breakdown field, now for the same voltage, you only need a much thinner layer of the drift layer, right? So you only require a much thinner drift layer to hold the same voltage. So all this extra resistance you can actually get rid of. Okay, so that's really the easy way to understand the advantage of using ultrawide bandgap semiconductor. So it's a reduction in resistance, and also a reduction in all this amount of charge which needs to be switched every time the device turns on and off. Okay, now in terms of application specifically, power electronics are required across the voltage spectrum, all the way from power supplies for our laptops and mobile phones to a lot of current applications like electric vehicles, data center power supplies, and very high voltage applications like locomotives, high voltage DC transmission, all that, right? Silicon and recently, silicon carbide and gallium nitride have sort of become, state-of-the-art materials, at least in the lower voltage till a kilovolt and a few kilovolts and so on. And, I think, as far as ultra-wide bandgap semiconductors are concerned, this is not just for gallium oxide, for other ultra-wide bandgaps as well. We're probably looking at, multi-kilovolt class applications. So we're really looking at high voltage applications for these semiconductors. And potentially also applications in extreme environments, right? So that's really where these semiconductors come in. So what about beta-gallium oxide? What is specific about gallium oxide? Well, gallium oxide has very good, attractive properties for power switching applications, right? So what are these properties? Well, you can get bulk, single crystalline, high quality substrates, which can be grown from the melt. You cannot do that for a lot of semiconductors, but for gallium oxide, you can do it. Classic examples are gallium nitride. Very difficult to do it for gallium nitride, but you can do it for gallium oxide. And people have reported, there are vendors who have reported 6-inch substrates. And of course, it's an ultra-wide bandgap semiconductor, so you would expect a high breakdown field. So the breakdown field for gallium oxide is somewhere around 8 megavolt per centimeter. And experimentally, people have approached at least closer to, so above 6 megavolt per centimeter, people have approached, and we're getting closer to that theoretical limit. And another key advantage is the wide doping range. So just because we have very high epitaxial quality, the substrates are very good, so therefore the epitaxial quality is very good. So the defect density is also very good, very low. So therefore you can essentially control the doping across a wide range, and you also have a shallow donor as well. So on the plot on the right, I'm showing some of the previous reports of gallium oxide in terms of the on resistance versus the breakdown voltage. So this includes both diodes and transistors, both vertical and lateral. And you can sort of see, it's not just at least, for gallium oxide, it's not just, promise in terms of theoretical figure of merits. People are actually reporting devices with, very good performance, approaching and exceeding silicon carbide and approaching gallium oxide. So these are at least, these are not quite large area devices, but these are at least, promising trend in the right direction. Now, at least for power electronics application, a key disadvantage for gallium oxide is the fact that, there's this lack of type doping. So that's certainly a disadvantage. And one of the areas that I'll discuss is trying to sort of address this disadvantage. Okay. So let me move on to my first topic today, which is on this new method of in situ damage-free etching of gallium oxide. So why would you need I guess low damage or damage-free etching? Well, you really require that for fabrication of devices, right? So there's a number of device structures. For example, the one on the left is a gate recess process where you etch down the gate region. The figure in the center is a vertical transistor structure, which actually have been demonstrated by Cornell University before, where you need to sort of etch down and make these fins. And the figure on the right is a lateral FinFET transistor, which was fabricated by the Air Force Research Laboratory. But the important thing here is you need good etch techniques to sort of make these three-dimensional devices, which are important for gallium oxide. And typically, most of these devices are etched using dry etching. There are also other techniques. So dry etching is one key technique which is used. There are also reports of wet etching using HF, phosphoric acid, KOH, and so on. But some of the key challenges with standard etching techniques, particularly with dry etching, is the plasma-induced damage. And many a times you get inclined sidewalls as well. You don't get straight vertical sidewalls, which sometimes you require in certain devices. But the key problem here is the plasma-induced damage, because you're really using a plasma to etch gallium oxide here. And then in case of wet etching, the problem is you have low controllability for wet etching. And since it's an isotropic etch process, you generally result in inclined sidewalls. So you get angled sidewalls, which you don't want many times. Okay. So if I think about an ideal etch process or a good etch process for fabricating 3D structures, I want the following to sort of happen together, right? So I want the etch process to give me vertical sidewalls. That's number one. It should be either damage-free or low damage, right? So that the devices can perform pretty well. And I should be able to control the etch rate. So it should be a controllable etching process. Okay. So this is where we've sort of tried this new technique. And the idea is to use, to use what is known as TGA, which is triethyl gallium, and to use TGA as the precursor to directly etch gallium oxide. So to do that, what you essentially do is you form a hard mask on gallium oxide, in which in this case we're using silicon dioxide, and you introduce this this sample into the MOCVD reactor. So this is a schematic of the MOCVD reactor, and then you introduce triethyl gallium. Okay, and the advantage of gallium oxide is gallium oxide tends to so there's a suboxide reaction between gallium oxide and metallic gallium, which actually results in the formation of a suboxide phase of gallium oxide, which is actually volatile at high temperatures. Okay, so you can consider this as a two-step reaction. So you introduce TGA into the reactor, and the substrate is heated now. So if the substrate is heated, the TGA undergoes pyrolysis and it releases gallium add atoms on the surface, right? So that's step one. And in step two, you're essentially, so the gallium actually reacts with gallium oxide through this suboxide reaction and results in the formation of this gallium suboxide. And the suboxide is volatile at reasonably high temperatures, so that dissolves from the surface, and that results in etching, right? And once your MOCVD etch step is done, you take out the sample, you can remove the hard mask, and you get the three-dimensional structure. So that's sort of this process, underlying process there. Okay. Now, since it's a since it's an etch process, that happens within an MOCVD reactor, there are a few key parameters that you can control, right? So one is the flow rate of the triethyl gallium. So, and the other one is the temperature, and then the third one is the pressure. And in this slide, I'm showing the effect of etch rate as a function of the TGA flow rate. So this figure on the left shows etch rate as a function of the TGA flow rate. And what is interesting is you get an almost linear increase in the etch rate. So it's the TGA flow rate is a very good control over the etch rates. So you get a linear increase, and eventually it saturates at high TGA molar flow rates. Okay, and the highest values of etch rates that we've obtained is around 8.5 microns, which is among the highest that's been reported for gallium oxide. So you can get very fast etch rates using this technique. And the figure on the right shows etch rate as a function of temperature. And again, you see an increasing trend as a function of temperature initially, and then eventually it's saturated. This is sort of a standard MOCVD process where initially at lower temperatures, it's limited by the reaction rate. At higher temperatures, it's just limited by the flow, which is the reason why it saturates. So this is standard, what you generally see for growth rates in an MOCVD reactor as well. But the important thing to understand is, so TGA flow rate is a good control, right? You can essentially use that to control the etch rate. So it's a good knob to vary the etch rate from low value if you require, or to a high value if you need that for the specific process. Okay. Now, since this is a chemical etch, what ended up happening is we saw quite a lot of anisotropy for this etch process. First of all, gallium oxide is an anisotropic. It's a monoclinic crystal structure, so we did expect anisotropy. So what we did to study this is to pattern these spoke wheel structures. So these are essentially trenches that are aligned in different crystallographic directions, for example, 001 or 100, 102, etc. And so these actually reveal specific crystallographic sidewall planes. Okay, if you orient these trenches in those directions, you're getting specific sidewall planes. And what we observed is, turns out most of the sidewall planes actually show rough sidewalls. So once the etches are done, the sidewalls actually are rough. For example, the ones on the right, the bottom right, the sidewalls are rough. But what we found is for the 010 gallium oxide specifically, if you orient your trenches in the 001 direction, so the in-plane direction needs to be 001, which is this direction. Oh, sorry, it is this direction. Then you get very smooth sidewalls. Okay, and the reason is the 001 sidewalls turns out it actually forms the 100 sidewall plane, which is actually the sidewall plane with the lowest surface energy. So if you orient your trenches in the right direction which shows the lowest surface energy, then you get very smooth sidewalls. Okay, And we see exactly the same trend when we looked at the 001 orientation of gallium oxide. Again, these are spoke wheel structures that we fabricated. And the figures on the right shows fins that are not oriented in the correct direction. So you see these rough sidewalls. But if you orient your sidewall in the right direction, so for example, this is the correct direction, and you get the 100 sidewall, then these sidewalls become extremely smooth. Okay. So this etching process provides you, provided you orient your devices in the correct direction, you can actually get three-dimensional structures with very smooth sidewalls. Okay. And we looked at this sidewall roughness a little bit more carefully. So what we observed is so this is the smooth sidewall that I was sort of talking about. And as you can sort of see, once you move away from this smooth sidewall direction, the sidewalls become progressively more rougher, right? And what's happening here is, if you look at this figure carefully, what's happening here is, so if you orient your, so let's say you form this trench on the top in this direction, since it's oriented in the 100 plane direction, you get an extremely smooth side. Okay. But let's say you try to make this trench, this bottom trench, which is not oriented in the correct direction. But because the 100 plane has the lowest surface energy, gallium oxide tries to form, to minimize the surface energy, it tries to form these 100 sidewall facets. Okay. And the larger this angle is, the denser these facets become, and therefore the roughness also increases. So as you move away from this smooth sidewall, you're essentially increasing the surface steps on your sidewalls, and that results in the higher roughness that we're seeing. So in addition to the anisotropy that we saw in the sidewall roughness, we also saw a key anisotropy in the lateral edge rate. So to understand, I have a schematic here on the top left. So when you etch gallium oxide using this process, there is a vertical etch depth that you obtain. But since this is an MOCVD process, CVD processes are generally more conformal, meaning you will also get deposition of gallium add atoms on the sidewall. So there's also a lateral etch component. Okay. So in addition to vertical etch, you also have lateral etch. Okay. So to understand this, we actually used what are known as these tapered spoke wheel structures. So these are the tapered spoke wheel structures. And so these have a small angle, if I call it some small angle theta, the angle that we used was roughly around 1 degrees or 2 degrees. And the idea is, so for example, if you have a lateral etch depth of x, then the fin length actually contracts by x divided by theta. Okay, so even if x is very small, let's say 100 nanometers, if the theta is small, the length contraction is actually larger, much larger. So you can essentially magnify the effect of the lateral edge. Okay, and so you can sort of see that effect here. So this is, so we've tried to characterize the lateral edge rate for 001 substrate. And as you can sort of see, the fins that have retracted the fastest or the farthest, they have the highest lateral edge rate. So the lateral edge rate is very high in these directions, but in the opposite direction, it's actually very low because the fins haven't retracted as far. Okay. And using these tapered spoke wheel structures, we were actually able to characterize the lateral edge rate for both the 010 as well as the 001 substrate. And we were able to see, the specific anisotropy. And there are certain directions which actually show very low lateral edge rate. So the plot here actually shows the ratio of lateral to vertical edge rate. And there are certain directions which actually show a ratio of around 0.1, meaning the lateral edge rate is actually not very large, right? It's only 10% compared to the vertical edge rate. And many a times you want the lateral edge rate to be small because you want the final dimensions of your devices to be similar to what you initially have in the mask, right? So therefore, ideally, you also want the lateral edge rate to be small. So these directions which show lowest lateral edge rate are probably good to sort of orient your devices. So we've used this understanding to actually fabricate some high aspect ratio fin structures on both the 010 and the 001 substrates. So on the top, I'm showing a fin array, a high aspect ratio fin array that we fabricated using this technique on 01001 gallium oxide substrate. And you can see that the fins are nicely arranged with very smooth sidewalls, right? We also try to do the same thing on 010 substrate, and again we get good fin, repeated fin structures or fin arrays. You can sort of see small steps arising. The reason for that was in this particular sample, there was a small misalignment of few degrees. So as soon as you have some misalignment, you start seeing these steps on the sides. Okay, so you want to make sure that your fins are aligned in the correct in-plane directions, or you start getting sidewall roughness. And in addition to just characterizing these the anisotropy, we also looked at the IV characteristics, right? That's very important to sort of understand if the etch process is damaging or if it's damage free, right? And to do this, we sort of fabricated 3 different diodes. So first one is a control diode, which is fabricated on a gallium oxide epi layer, which did not undergo the etch process. Okay, remember the etch process is done at high temperature. So this control Schottky diode is not exposed to the high temperatures. Okay. Now we also fabricated 2 other diodes. One is the etched Schottky diode, which obviously is, as the name suggests, after the TEG etching, you fabricate diodes on the etched surface, right? We also have these unetched Schottky diodes, which are essentially regions which were initially masked using silicon dioxide, and the silicon dioxide mask was later removed after the etching process. So that's the unetched Schottky diode. Okay, and so this is a comparison of the current density, the IV characteristics of the diode for each of the 3 diodes. And what you see is that the control diode and the etched diode actually show very similar characteristics. And the etched diode actually shows lower leakage current compared to the control diode. Okay. Now, the interesting thing here is the unetched diode actually shows a reduction in the Schottky barrier height. And we're still not sure why, what the specific reason is. But it could be that the silicon dioxide masking. So this region, which was masked with silicon dioxide, when it was exposed to high temperature, there was some change in the surface morphology, which probably caused this in the barrier height. Okay, but the important thing is the etched surface looks pristine. It looks as good or if not better compared to the control diode. So we can essentially confirm that this whole process, this TEG etch process, is pretty much damage free. It's non-damaging to the underlying material. Okay, so that's that's it about the in situ damage free process. Now I'll talk a little bit about our work on the nickel oxide, gallium oxide diodes, the engineering of these diodes. So as I mentioned before, key disadvantage in gallium oxide is the lack of inherent p-type doping that you can do in gallium oxide. So it's very difficult to get p-type gallium oxide. Okay, and what people have or what researchers have done is instead of using p-type gallium oxide, you essentially integrate gallium oxide with other p-type oxides. So for example, here a standard one that's used is p-type nickel oxide. There are also reports of other p-type oxides such as chromium dioxide or copper oxide that people have used. And essentially, these are not epitaxially grown, but these are instead sputtered. So the p-nickel oxide is sputtered directly on top of the gallium oxide layer. So this is a standard structure of a p-nickel oxide N-gallium oxide heterojunction. Okay. And so the idea is to, instead of forming a homo p-n junction, you're essentially forming a hetero p-n junction using these p-type oxides. So this is a schematic band diagram for this hetero p-n junction. And what is typically observed is a staggered type 2 band alignment with a conduction band offset of around 1.5 eV. And built-in voltage is typically exceed 2 eV for this heterojunction. Okay. Now, the key advantage of, or at least what other researchers have found, is the key advantage of using the structure is that it offers high breakdown field. Just because the built-in voltage is much larger, the breakdown field that it can actually sustain at this junction seems to be much larger compared to a standard Schottky diode. And another advantage is that this junction also offers lower reverse leakage, particularly at elevated temperatures. So it's a little bit more thermally stable compared to a standard Schottky diode on gallium oxide. And in this plot on the right, I'm showing the on-state resistance as a function of breakdown voltage for different gallium oxide devices that's been reported previously. And as you can see, many of the devices which actually show very good performance in terms of the figure of merit are actually devices which utilize the p nickel oxide gallium oxide heterojunction. So these have been experimentally shown to offer good breakdown performance. Okay. But what is the disadvantage? Well, the disadvantage is the fact that the turn-on voltage for these diodes is generally higher, right? So this is a schematic that shows a linear IV characteristic for comparison between a Schottky diode on gallium oxide and these kind of heterojunction diodes. So Schottky diodes typically turn on at 1 volt roughly for gallium oxide. And what's been observed for heterojunction diodes is that the turn is typically much higher, typically higher than 2 volts, which generally you don't want to have such high turn on voltage, because remember, the voltage times the current. So anytime you have a turn on voltage, that adds power losses to your device, which you don't want to incur, right? So you technically want this turn on voltage to be as small as possible or closer to this Schottky diode. And so the work that we've tried to do is we've looked at approaches to sort of reduce this turn on voltage for the heterojunction diodes, but at the same time, looking at sustaining the same amount of breakdown voltage. So keep the same breakdown voltage, but reduce the turn on voltage. And this is where we looked at this junction barrier Schottky diode. And this is a standard design that's used in materials like silicon and silicon carbide. And our approach really is so the device structure is sort of shown here. The idea is you etch out these trenches, and you essentially form two different junctions on the same device. So I have at the bottom of the trench, and on the side walls, I have the nickel oxide gallium oxide junction here. And at the top of the fin, I have a Schottky gallium oxide junction. So I have two junctions. And the advantage of this is, so when you forward bias the device, both the heterojunction and the Schottky junction, both of them are forward bias. But since the Schottky junction has a much lower turn on voltage, the Schottky will turn on first and will determine the current in the device. Whereas when under reverse bias, turns out the electric field is actually entirely blocked by this bottom junction, and I'll show some TCAD simulations. Just due to this fin structure, turns out the field is entirely, or the voltage is entirely blocked by this bottom junction. So essentially, you get the advantage of the forward bias. In the forward bias, you get the advantage of the Schottky. In the reverse bias, you get the advantage of the nickel oxide gallium oxide junction. Okay. So this is just a TCAD simulation of the nickel oxide gallium oxide JBS diode. So the simulation is done at 2 kilovolt. And you can essentially see right from the contour plot that, so this is a contour plot showing the electric field profile at 2 kilovolts reverse bias. And you can essentially see at the, you're closer to the Schottky contact, which is here at, closer to this point B, the field is very minimal, right? So all the field is sort of at this nickel oxide gallium oxide junction, which is good, right? Because that's the junction that can sustain the higher field. Okay. Now on the right, I have two cut lines. So A prime is this lateral cut line. So you can see this shows field of around 3 megavolt per centimeter, and the peak being 3.7 megavolt per centimeter right at this corner. And I also have this B prime cut line, which is a vertical cut line all the way from the bottom all the way to the top of the Schottky contact. And you can sort of see right at the Schottky contact, the field is actually very small. This is specifically for a 0.6 micron trench and a 1 micron trench height. This surface field is essentially manageable. You can essentially change it by changing the aspect ratio of this fin. So this is pretty much controllable. But the important thing is that the surface field is significantly low, right? So you can significantly reduce the surface field. Okay. Now, we've sort of talked about, controlling the field at this junction, but remember the field, device also has an edge, and you have to sort of manage the electric field at the edge of the device also. Okay. And in this specific case, we actually looked at what is known as a space modulated junction termination extension. So typically to protect the edges of your device, you use edge termination structures. So in the figure on the left, I'm sort of showing a 1D, one-dimensional nickel oxide, gallium oxide diode, and what you can sort of think about as an ideal junction termination extension. So in this case, the thickness of the nickel oxide is gradually decreasing away from the edge of the device. And what this does is, so this will allow you to gradually reduce the depletion region from the edge of the device to the edge of the JTE. Okay. And that generally gives you the best, junction termination efficiency. Now, this is, I don't want to say that this is not achievable, but it's a bit difficult to achieve, this kind of a tapered profile over a long distance. And so therefore, what we went instead with is the space modulated design, where we're actually using these nickel oxide rings. So we are using multiple rings, but we are sort of varying the spacing and the width of these rings. So initially the width is large, but the width gradually reduces as you reach, as you go farther away from the anode contact. So you're essentially sort of modulating the charge in the nickel oxide layer and sort of reducing it on average from some high value at the anode edge to a low value at the edge of the junction termination extension. Okay. And so this, we were trying to sort of emulate or trying to replicate this kind of an ideal junction termination extension without having to sort of go through fabricating such a structure. That's sort of what this space modulated junction termination extensions do. Okay. So this is a figure of, so this is an optical image of a fabricated space modulated JTE, where you can sort of see the rings and the gradual variation of the rings as you go away from the anode edge towards the edge of the JTE. Okay. And this is a TCAD simulation of the, of just the junction termination extension, the space modulated JTE. And this is the, I'm simply showing the optimized structure here, which is done at, so this is for 3 kilovolt. And you can essentially see that the electric field is the edge term, the electric field at the edge of the device is pretty well managed, right? So at the center of the device, it's a little less than 4 megavolt per centimeter. And at the edge of the device, it's slightly above 4 megavolt per centimeter. But you're not seeing, very large peak electric fields in this device. And if you convert that to a JT efficiency, you get around 90% for this optimized structure. So our final JBS diode, we sort of combine the trenches along with this junction termination extension to have our final devices. So in the center of the device, you have these trenches, which is the active region of the device. This is where the current will pass. And the edge termination essentially sort of, is done to sort of mitigate the peak electric field at the edge of the device. Okay, so this is the final device structure. And the fin widths that we've used for the specific study, we've used 0.6 all the way to 1.5 micron. So this is a little, we've kind of used small fin widths. And the fin spacing that we used was 2 micron. And the total nickel oxide thickness is roughly around 150 nanometer. Okay. And so this is a process flow that we've used for the, specifically for the trench region. So what we did, we used a bilayer stack of dielectrics. So 300 nanometer silicon nitride and then silicon nitride on top, 100 nanometers. And then we first used this hard mask to etch the gallium oxide. And then we use a clever BOE etch to actually sort of form this kind of an undercut structure. So remember, BOE etches silicon dioxide much faster than silicon nitride. So you can essentially get this kind of an undercut structure using BOE. And then you deposit nickel oxide. And because you have this nickel oxide because you have this undercut, it's much easier to do the lift off of the nickel oxide from the top of the fin. And finally, you just deposit the Schottky contact like that. Okay, so that's the process flow. I'm just showing the process flow for the trench region, not showing it separately for the junction termination extension. Okay, so this is showing the electrical characteristics of the fabricated devices. So this is a comparison of the Schottky diode, which is a planar Schottky diode that we fabricated on the same device. We've also fabricated a planar heterojunction diode. And then the 0.85 micron device is the JBS diode with a fin width of 0.85 micron. And what you see is, the heterojunction diode turns on at around 2.5 volts, not great. The Schottky diode, which is the black one, turns on below 1 volt. Whereas the JBS diodes that we fabricated, the turn-on voltage is actually around 1 volt. So it's in between that of the heterojunction diode and the Schottky diode. It's much closer to the Schottky diode, which is sort of what we want. Okay. And this is a comparison of the current density as a function of voltage for the different fin widths that we've used. And of course, the smaller the fin width, the lower the current and the higher the on resistance. And what we observe is as you go above 0.85 microns, then we don't see significant differences, very large difference in terms of the on resistance. So the 0.7 micron or 0.6 micron are probably not very good for this particular structure or the nickel oxide that we're currently using. And we also get good on-off ratios for the JBS diodes. So here we're looking at specifically the electrical characteristics in terms of the breakdown voltage. So we broke down these devices. So the important thing to note here is, so as a baseline, we measure the breakdown voltage for the planar heterojunction diode, which turns out to be around 900 volts. So the heterojunction diodes break down around 900 volts. And the planar Schottky diode, they seem to break down around 500 volts. Okay. Whereas the JBS diodes, they show a much larger breakdown voltage of around 1.8 kilovolts. Okay, so all of them show good breakdown performance, much larger, almost 2x higher than the planar nickel oxide diodes. And what this tells us is, okay, the trench design and the field termination are actually working. But one thing this is showing is that this, we were finding that there isn't much of, in terms of the breakdown, we don't see much impact of the fin width, at least on the breakdown voltage. And what that is saying us, or what that is telling us is that the breakdown is actually just limited by the nickel oxide gallium oxide junction. It's not limited by the Schottky junction. So breakdown is limited by this junction and not the Schottky junction. Remember, as you change the fin width, it's really the surface field that reduces. So this field has a minimum. So the fin width has a minimal effect on. Okay. And in terms of the figure of merit, if you convert the on resistance and the breakdown voltage into figure of merit, we get roughly 0.7 gigawatt per centimeter square. Again, this is not a world record number, but this is sort of in the right direction as far as we are concerned, and particularly considering that we also get lower turn on voltages. Right, so finally, I'll move on to the last section, which is sort of focusing on gallium oxide for RF electronics, and particularly our recent work on getting FinFET devices to work on gallium oxide. Okay, so why would you look at gallium oxide for RF transistors? Well, there are some obvious advantages. One, of course, is the fact that you have a high breakdown field for gallium oxide. And what this really does is, the higher breakdown field generally gives you a higher power triangle for RF devices, and that can potentially sort of translate to higher output power density for power amplification, right? And gallium oxide also has the ability to form heterostructures. So this is essentially plot from Hari's group. You can sort of get mobilities close to 200 centimeters square in 2D electron gases. So you can essentially form these aluminum gallium oxide heterostructures and get 2D electron gases, which are vertically scaled channels, right? So and get reasonably good performance. Another key advantage, which I think is very important, is the fact that you can get very high doping concentrations in gallium oxide, which in many of the other ultra-wide bandgap semiconductors you really cannot do. So this is an example which is showing the contact resistance that's obtained to the underlying doping concentration in gallium oxide, and you can see doping concentrations. You can easily get 3 times 10 to the 20, which is very difficult to achieve in, let's say, material like aluminum nitride or high composition AlGaN, which is generally an order of magnitude lower. And what this translates to is much lower contact resistance that you can get in gallium oxide, which I think will be an advantage for gallium oxide going ahead. Of course, everything is not rosy, right? So there are some key challenges, particularly for RF. The key challenge is the low thermal conductivity. So you really have to manage you really have to thermally manage the device and the wafer to really able to sort of maximize the performance of gallium oxide. Although in this particular talk, I won't be sort of focusing on the thermal conductivity aspect. And the second difficulty with gallium oxide is the lower mobility compared to, let's say, gallium nitride. So this results in much higher sheet resistance for the channels, which results in non-ideal characteristics as well. So this is sort of a summary of some of the state-of-the-art performance for gallium oxide. So the plot on the left is showing reports of gallium oxide devices. These are all lateral devices in terms of breakdown voltage and cutoff frequency. And the cutoff the frequency performance is somewhat limited. The maximum is around 40-45 gigahertz. The breakdown voltages are already pretty good, right? So everything is most of the reports are above 100 volts. So as you would expect, gallium oxide is giving good breakdown performance, but yeah, frequency performance is kind of lagging. So that needs to be taken care of. And of course, the reason is you're not essentially getting, the theoretical electron velocity from, these gallium oxide transistors. So this is a plot of electron velocity versus gate length. Again, these are previous reports, right? And these are estimated from either the cutoff frequency FT or the transconductance. And what is typically seen is even the highest report is roughly around 4 times 10 to the 6. That's the effective velocity that's been reported. So, we need a lot more engineering to take this from 4 times 10 to the 6 to closer to the theoretical, saturation velocity limit. Okay. And so this is the plot on the right is showing the output power that's been reported. So this is power density as a function of frequency. The red ones are actually gallium nitride reports. So you can see, these are state-of-the-art reports from gallium nitride, and the blue dots are actually gallium oxide. And the state-of-the-art is only around 2 watts per millimeter, and that too at 2 gigahertz. So it's so the state-of-the-art is well below that of aluminum gallium nitride HEMT at present at least. Except, of course, the breakdown voltage is looking very promising. But all other characteristic needs to be improved. So a lot of engineering needs to happen. Okay. And here I want to sort of particularly focus my attention to a key challenge, which is the issue with the source resistance. So what is source resistance? So if you can sort of combine all the resistance in series to the left of the gate. So this is only showing a zoomed in image of the gate to source region of a lateral transistor. So if you add up all the resistance to the left of the gate, then that's your source resistance. So in a very simple way, you can, if you add the total contact resistance plus the resistance between the source and the gate, that's your source resistance. And why is it important? Well, it turns out the extrinsic transconductance, which is actually what you measure, turns out to be inversely dependent on the source resistance. If the source resistance is very high, your extrinsic transconductance is going to be very low. Okay, so this needs to be critically managed. And why is source resistance much more important for gallium oxide? Remember, gallium oxide has a much lower mobility compared to, let's say, gallium nitride. So therefore, any small distance that you have between the source and gate, it may not be an issue for gallium nitride, but it's going to be an issue for gallium oxide. Okay, so this is a plot of extrinsic GM versus intrinsic GM for different values of source resistance for 10 ohm millimeter, 5 ohm millimeter, 1 ohm millimeter, and so on. And as you can see, you really should be looking at getting close to 0.1 ohm millimeter source resistance to really get good extrinsic performance, extrinsic transconductance from gallium oxide. So typical gallium oxide devices are in this range of roughly around 5 ohm millimeter to 10 ohm millimeters, which means you're really undercutting sort of the extrinsic transconductance. Okay. So we should look at approaches to sort of achieve close to 0.1 ohm millimeter, source resistance or thereabouts, right, to get high intrinsic transconductance. And in this approach, what we've done is we've tried to focus on high charge density channels. Okay, one way to sort of reduce the source resistance is to use a high charge density channel. Right, the higher the charge, the lower will be the resistance. Of course, you can't just use a high charge density channel. You have to sort of be able to modulate it. So we decided to use a FinFET design also to be able to modulate the high charge density. Okay, and so these samples were grown at Cornell. So this is the structure that was used. So this was grown by Dr. Heidi's group at Cornell, and so we're essentially using a silicon delta doped channel with a very high charge density. So we're using a charge density of around 3.3 times 10 to the 13. And based on the measurements that we've done, so this is the data point for the charge density and mobility. So the mobility that we got for this specific sample was roughly around 90 centimeters squared per volt second. So why are we using silicon delta doping? Well, silicon delta doping allows you to get confined, spatially confined channels. And it's also very easy to sort of change the channel, charge concentration. So if you want to get low charge concentration, you can just vary the silicon concentration. If you want to get high charge concentration, you just increase the silicon concentration to a first order at least. So which is the reason why we went with the silicon delta dope. Okay, so this is just a process flow that we've used for fabrication of the submicron fins. So we've specifically used a bilayer mask. So we used ZEP, which is an e-beam resist. It's a little bit more resistant to dry etching. And we also use the silicon dioxide hard mask. Okay, so first we used e-beam lithography to fabricate fins, and then we used wet etching to actually etch the silicon dioxide. And then we used a specifically sort of a modified, a very slow dry etch process for gallium oxide to actually etch into the gallium oxide and form these fins. And then we use ALD Al2O3 as the gate dielectric, and then finally deposit the nickel gates. Okay. So these are SEM images of the fins. So the figure on the right is fins after the etching process and removal of the mask. And then the image on the left is actually the fins after the nickel gate has been deposited. So this is the gate, this is the source gate, and this is the regrowth that we've done. Okay, so this is discussing looking at the charge profile here. So we were able to extract the effective charge profile from capacitance voltage measurements. And we get a reasonably sharp profile with approximately a Gaussian profile, and the full width half maxima that we got was around 8 nanometer, which is pretty good. We would like to move. We would like to be much sharper in the future, but this is a good start. And the figure on the right is the TLM measurements that we've done, looking at the total contact resistance, which is the contact resistance from all the way from the metal to the channel, right? And we get good linear fits and a very low contact resistance of 0.4 ohm millimeter. And this is primarily due to the high charge density that we're using. And then also due to the fact that we used a very low etch process to actually etch into the gallium oxide. So we used a specifically low etch, low power process to do this recess etch for the contacts. Okay. And in terms of the IV characteristics, we were able to get very good, current densities exceeding 400 milliamp per millimeter, which is actually the highest reported for gallium oxide FinFETs. We also were able to get an on-off ratio of around 10 to the 9. And remember that this is modulating 3.3 times 10 to the 13 charge density, which is also a record high. So very high charge density and simultaneously getting such good on-off ratios. So both of, so both of these are very good numbers to go by. And a peak transconductance of around 60 millisiemens per millimeter. Again, this is an ongoing work. So we're looking at pulsed IV and other characterization, RF characterization, and so on, to further study this FinFET devices on gallium oxide. Okay, and so with that, I'll end my talk and I'll just summarize. So what I've discussed so far is the in situ TEG etching that we've demonstrated. It looks like a very good technique if you want to make smooth sidewalls. It's also damage free. And another key advantage is it's in situ, right? So you can do everything within the MOCVD reactor. So you can etch and then potentially regrow, right? So that's an advantage of that technique. We've also been able to fabricate kilovolt class diodes, particularly junction barrier Schottky diodes with low turn-on voltages. And we've also designed this new space modulated junction termination extension, both of which show very good promise for vertical gallium oxide power devices going forward. And recently, we've also been able to achieve high performance gallium oxide FinFETs. Hopefully, that can be taken in the future towards high performance RF devices for gallium oxide, particularly focused on high charge density channels. Okay, so and then with that, I'll end my talk and I'll take any questions that you have.